Hello everyone watching this video. Today in this video we will discuss the moment of inertia for a hollow sphere. So first I draw a hollow sphere and here it is a hollow sphere which outer radius is R1 and inner radius is R2. So here this is a hollow sphere which outer radius is R1 and inner radius is R2. So you can say, so this area, this particular area between R1 minus R2 is filled with mass capital M and density rho, and this volume between the radius R2 is completely empty. So this is the hollow sphere, and we can imagine that this was the complete sphere of radius R1. We took out a sphere of radius R2 from it and we got this hollow sphere. So for this we will determine the moment of inertia, and in first case we will take an axis along the diameter and passing through its center. So this is the axis. In first case, about it we will determine the moment of inertia. So this is our first case, or this is our axis. In first case, about it will determine the moment of inertia. And in first of all, we can write the mass also that will help you in the derivation. So first we will write the mass of this hollow sphere in this form, that 4 by 3 pi R1 cube minus R2 cube into rho. So this is the volume of this sphere, which is 4 by 3 pi R1 cube minus the 4 by 3 pi R2 cube, and here it is the density of this sphere. So this is the mass of sphere which we will require in further derivation. So here, okay, I said that we can assume that in beginning this was a complete sphere which was in which mass was distributed continuously, and we can say this was a complete solid sphere of radius capital R1. Then the moment of inertia about this axis for the imagined solid sphere, we can write in last video we derived the moment of inertia for a solid sphere, so which is 2 by 5 m1 r1 square. So m1 is the mass of that we assumed the solid sphere of radius small r1, and the moment of inertia along the axis, for axis along the diameter for a solid sphere is 2 by 5 mr square, and m1 for the solid sphere of radius r1 and radius is small r1. Now we imagine a sphere of radius R2 here, which is also a solid sphere, and the moment of inertia along this axis for the inner sphere will be I2 equals to 2 by 5 m2 R2 square. So here we have two moment of inertia for a complete sphere, and this is the moment of inertia in the a small sphere radius R2, and here we have a hollow sphere which is we get when we have a complete sphere of radius R1 and we take a sphere of R2 out from it. So here we have two formulas for two sphere, and the moment of inertia for this hollow sphere will be I1 minus I2, and this is the equation we discussed previously, that we can add the moment of inertia and we can subtract the moment of inertia, but the axis should be equal. So in first case we took the moment of inertia for complete sphere, and second case we took the moment of inertia for this sphere, the small sphere between it, and for hollow sphere we need the moment of inertia for this mass. For that we will subtract moment of inertia for this mass from the moment of inertia for complete mass, and we'll get the moment of inertia for this mass between two radius R1 and R2. So here our moment of inertia I will be I1 minus I2. We can write it the value of I1 and 2 here, and value of I1 is 2 by 5, and in both of the cases 2 by 5 is constant, same, so we take it common and we'll write m1 r1 square minus m2 r2 square. Can we put the value of m1 and m2? Yes, we can. We know the density of this sphere, these two spheres, so we write the first value of m1, our mass of m1, the complete sphere is 4 by 3 pi r1 cube. So this is the volume of complete sphere, and we know the density of this sphere, or we assume that rho, and here r1 square again minus the volume of m2 is 4 by 3 pi, the radius r2 cube into density, and here the value of r2 same, so we get this I is 2 by 5 4, and here the m1 r1 square and m2 r2 square. We solve it and we get the constants out, so we'll get I will be, here I can write 2 by 5 is here, and I take this thing common, the 4 by 3 pi, and here r1 cube and into rho also r1 cube minus r2 cube into rho also. So I write it in this form so that I can take something out. I can take the value of m here. So 2 by 5 is here, 4 by 3 I took out a constant, and pi here, and rho is here. So, and remaining part is here the square and here cube, it will become r1 power 5 minus the square and cube will become r2 power 5. So this is the equation we get from this equation, but here we will derive the moment of inertia, and for that you know that in any moment of inertia formula we need a mass. So here we have the mass m, and we will convert the value of mass here. So for that we will multiply the r1 cube minus r2 cube in this equation at the numerator and denominator both. So I will become 2 by 5, and I can write it here first r1 power 5 minus r2 power 5, and this value is 4 by 3 pi into rho. Now I multiply something here, which is r1 cube minus r2 cube, and at the denominator also r1 cube minus r2 cube. So here this is the mass of this hollow sphere. So I will be 2 by 5 capital M, that this is the mass, this is the mass of this sphere, and here r1 power 5 minus r2 power 5, and in denominator r1 cube minus r2 cube. So this is the moment of inertia for a hollow sphere of outer radius r small capital R1 and inner radius capital R2 about an axis along the diameter. So this is the moment of inertia for hollow sphere, and in a special case is here, special case if R1 is capital R and R2 is 0. This means R1 we are taking capital R and R2 is 0. That means we are assuming a complete sphere. So when we put the value in this formula, so I will become 2 by 5 capital M R2 will become 0, and here also, and this it will become R square. So this is the moment of inertia for a solid sphere, where we take R1 is capital I and R2 is 0. Means we are taking none out of a complete solid sphere, then we get a solid sphere, and moment of inertia for that 2 by 5 mr square. So this is our first case, and in second case we take an axis along the tangent. So here we first change the case along the tangent. So I clean it first, and I just tell you this is the axis about which will determine the moment of inertia here. So I can write it, the moment of inertia about this axis I naught, which we derived here, and in this case we will derive the moment of inertia about this axis or along the tangent. So in this case we can see two parallel axes. So here we will use the parallel axis theorem, and according to parallel axis theorem, the moment of inertia of an axis is equal to moment of inertia of the parallel axis plus md square. So I will determine I naught we have derived, which is 2 by 5 m r1 power 5 minus r2 power 5 upon r1 cube minus r2 cube. So this is the moment of inertia about the main axis, and plus m here is the mass of this sphere, and the d is the distance between two parallel axes, which is r1. So r1 is square. So this is the moment of inertia about an axis along the tangent, and this is the moment of inertia about an axis along the diameter for a hollow sphere. So today we wind up this video here, and please make the notes and revise your syllabus continuously, and best of luck for the next video.